Thanks. Okay, so this is our third session on Cassandra, and we are going to discuss whatever is left over. So now, for I think we covered most of the Cassandra's read, write, everything earlier, and then we did about the replication, the high-level architecture, the consistency levels, and the gossiper. And now today we will be discussing more about what compaction is and how it is implemented and bit of some more details about it. But I would say it's still very superficial, and everyone, if you wants, is more interested in understanding because it's very complex, and the more detail you go, you will understand a lot of stuff, and then you'll have to dig down more. So to be very simple, we'll try to really understand what compaction is and the different ways to do compaction. And also we'll touch base on Tombstone and how tombstones are and why the need of tombstones. Okay, so now to start with the compaction. So why we need a compaction? So to go to that, let me go back to what we were discussing earlier, right? So this is the right path. And we all know that writing is more easier in Cassandra. So the way it is like, whenever you get a write request, we just have to write first to a commit log, which is in the disk, and then to a mem table, which is in the memory. And then rest is taken care by the system, right? So the mem table actually keeps on whatever the data is, it keeps on accumulating for a certain size. And when that is done, it will actually flush to an SS table, which is stored on the disk. So this is a process. And then we'll have a continuous series of SS table. And then the problem starts happening, right? Because we'll have mem table whenever it is done, its size, then it will flush to the SS table, then but it will create another mem table. So the size of SS table keeps on increasing. So for write, it doesn't matter, right? It just has to write in commit log and the mem table and it's done. But when you go for read, so what happens here? So in the read, actually, it's not so straightforward. Okay, so what we have to do in a read is we also have to look for a mem table if the value is there in mem table. If it is not, then we have to go and look for the value in SS table. And for that, we'll have to look in an SS table, in many SS table, because SS table will have partitions stored across. So you'll have to go to all the partitions which are area of interest. And in those partitions, we'll have to find the data. So you'll be reading multiple of SS tables. And so for that, they have used many optimized techniques like Bloom filter. Bloom filter will actually point us, and it will give us whether the data is not present or is present. Okay, if it says it's present, it may be or it may not, but if it is not present, it means it's not present. So we can use Bloom filter, but still you'll have to go to the partition summary, then the partition index, go to a particular SS table in in your in the disk, and then you'll have to go to many of the SS table and then look for the area of the data what you're looking for. So that involves a lot of things in the read request, right? So therefore, we'll have to be optimized more about these SS table. And also, if you look at it, the MM tables and SS tables are maintained per table, and SS tables are immutable. So whenever you write a mem table is flushed into SS table, you are not going to change the SS table. So what will happen is you will have multiple SS table, and therefore when you have multiple SS table, so we have a performance hit on the read side. And for that, one way would be like, if they are immutable, then how do we actually try to combine them? So if you combine them, at least it's going to have a it will reduce the space as well as the complexity of reading, correct? So that is why actually we need compaction. And therefore, if you look in this example, okay, so these are maybe like two SS tables. Okay, let me annotate here. Okay, so if this is SS table 1, okay, and if this is table 2, and just imagine these are the indexes, okay, so 2, 4, 5, or the partition keys, whatever you can call them. So, and we all know that SS table, everything is in a sorted form. So if you look at all um, these partition keys are in the sorted form, and also you have another SS table too, which is also in sorted form, and they are roughly of the same size. Then we can actually combine them together in a single SS table, which maybe we call it as A. Okay. So then, but when we do it, more efficiently, we can actually merge them because both of them are sorted, right? So when we do that, we actually have merged SS table. And also what we do in merge SS table, if you look at this 9 key over here, okay, so this is actually, it is said it is a tombstone. It has been declared in the SS table 2 as a tombstone. So it means that you have this 9 can be deleted. Okay, so therefore if you look at the one which we have compacted or merged, so you don't see the 9 over here. So actually we are trying to even reduce the space size as well as efficiently use our disk optimization, right? So that is one thing what we have to look for. So it will reduce the number of SS tables, and also it will reclaim whatever the space is from actually the older data in a SS table. Correct. So this is what actually compaction is. And so any questions, anyone?
The Tombstone, that is good. Good.
Yeah, same question I was having. Maybe you can go ahead.
I'm saying Tombstone does lazy deletion, right? Like it's present in first and in second. I mean, it should have been. It was supposed to be deleted in the first SS table only, right? But it got converted to Tombstone in the second SS table, right?
Well, okay.
So, like,
okay,
even if things are deleted in Cassandra, it's not immediately washed away, right? I think it
right. So there are different strategies actually of how it is implemented. But just to give a high level overview of what compaction is, so just taken an example of 9 as a tombstone, and we don't want that 9 to be present in the
compact.
Yeah, the compacted SS table, correct. Yeah. So, but we have 1 and 2, and just imagine these both two SS table are these are the current SS tables, and then we want to merge them together. So there are different strategies actually of compaction. So we'll go to that also. At least we'll cover in a very high level. And the compaction is really not so easy, even if it looks like, because we keep on creating SS tables, and then we keep on compacting them also. And then if the size keeps on growing, so how long we have to keep on compacting them, right? So they follow some strategies. To some extent you are able to understand, you get a gist of it, but frankly there is still some questions. Maybe if we really go in deep and read, if we are really interested about it, then we'll come to know. But let's really go in only whatever the high level is there. Okay, so this is okay. Let me remember. Okay, so here actually the compaction they have discussed about it is like all the details, how it's merged, and then how it is done and all that stuff. And then we have some of these strategies, or the compaction strategies. So the one way, the first thing actually is discussed everywhere is like size tiered compaction strategy. And there are actually 3 of them. All right, okay, let me go to this one. Or this one, I think it should be here. Okay, so yeah, there are 3 major ones. Okay, so they actually discuss the 4th one also, but actually it is said it's deprecated in the newer versions of Cassandra. So one is the level compaction strategy, other is the size tiered compaction strategy, and the third is the time window compaction strategy. And some of the details in, okay, for this is the basic one and by default. So what it says is, like, if we have a few SS table, okay, and of the same size, then we actually compact all of them together in one SS table, and we create a bigger one. And by default, they are actually taking the number, the number of those table, like 4. So if there are 4 SS tables of certain size, they are actually merged together, so they form a bigger SS table. So that compacted SS table also is not of the same size of all the 4. It might be slightly bigger than an individual SS table, but it might be slightly lesser than combining all of them together, right? So that is what actually this says. But in this case, this is good strategy, because it is good for if we have heavy writes, because if we just compact all the 4 and then we move ahead, right? But the problem will come for a write in this case, because see, if you have 4 of these SS table of same sizes, and then we are compacting them and into a bigger one, but that compacted one SS table will have a partition, some partition, whichever we are interested in. But if we want to look for a particular data, so we'll have partitions spread across many of these compacted SS tables. So we'll have to look for each of these compacted SS tables which have the partition of interest, and then we'll have to get a data from it and then do the same stuff, right? So therefore it is good for write based one, because here we just write it and then it is taken care by the compaction, but we don't have to bother. But it has slightly hit on the read performance. So for the read performance, what they say to get a better way of doing read is, like, you use a leveled compaction strategy. Okay, so before even going for the leveled one, I'll just show you the size tiered, which is slightly explained here in a diagram form. And what it says is here, it initiates a compaction when Cassandra has accumulated a number of similar size SS tables. Okay, and so by default it is set to 4. So when we have 4 of them, and then it produces an SS table of one larger SS table, so combining 4 together. So, and then as these larger SS table accumulate, okay, so then what will happen if we combine all the 4 together? So it may be roughly around 4x of the previous table. So another SS table of same 4x size, if we have 4 of them together, they will again combine together, and then they will form another SS table of a 16, something like that, right? So therefore you'll have a compaction of many, after many inserts, you'll have roughly around so many SS tables of various sizes. Okay, so and then again, if you want to combine them, so you'll have to see if either of them are of the same size, then you again combine them and they form another larger SS table.
We only combine if they are equal size.
Yeah, that is what it says, roughly around that.
Oh,
So the
not
last
of similar
last
sizes tables.
yeah. So the last one will become very big, right? I mean 4x, 16x, then 16, 16 you will find, right?
Right.
16.
Yeah, but then if you look at eventually, it will actually, there might be some way to limit it, because it cannot cross the disk boundaries, disk size, right? Yeah. So there might be some techniques, and therefore I'm saying, all these are very high level concepts what they're trying to, give us. But because there will be tons of questions after that, we'll come to know, we'll uncover, right? So the way you said. And so what the answers are, there are a lot many theories about it, and then if you keep reading it, it's endless, right? So we'll have to stick to some extent. We'll say, okay, now we have this much, we combine 4 of them together and then we move on, then the thing keeps on increasing. But then how, I had also one question, like if I'm in the middle of like this SS table, and if I get all of them of 4, so does Cassandra start a process which keeps on monitoring all the SS table sizes, or it is, but this SS table strategy is only initiated whenever you flush a mem table into an SS table. Okay, only at that time. So is that actually keeps on looking for all of them together, or only it clubs the first 4 and forgets it? Then if it is
So
doing so,
since it's a string, I mean sorted, it will be sorted, no? So I mean SS table is a sorted string table, right?
Right. So it is,
So
compaction is always easier, but so if you see, these are all sorted SS tables, but they are of varying sizes. So whenever a new SS table, even if we just assume that these are all compacted and merged one, okay, but then this compacted again have to be compacted further if they actually keep on increasing in the size also, isn't it?
yeah.
So that is the reason it shows so much of varying size of these SS tables. So how it is going to end, that you asked, that is not very clear. And also, like, if in between, if there are some 4 of the SS tables which are of the same size and they have a larger one, like in this case, this one, right? And then how it is actually, how it initiates a compaction at that time. So in this case, if I had 4 of them, right? So for this particular cell, so is there a separate process which keeps on monitoring all of them, or it is only done whenever we actually flush a new SS table? So those things are not very clearly said everywhere. So yeah, so that is what it is. They just say this is the basic by default what they use. But even if you for this one, it says the SS table works well to compact a write intensive workload, and it makes read slower because the merge by size process does not group data by rows. Okay, so because what happens if I'm looking for a particular data of interest, so I will have a partition interest of my partition over here, also here, or maybe here also. Then what I'll have to do is I'll have to look for all of this partition and find my interest of row key, and that particular data or the cluster index and all that stuff, right? So that will actually involve reading all of these SS tables, and therefore it will have a what you say, it will make read slower. That is what they are trying to say. Okay, so for what you say, read intensive workload, what it is said is it is better to follow an LCS. Okay, so now what is the LCS? LCS is it says that it is a level by level. So we have something like this various levels like L0, L1, L2, and L3, and in each level you will have 10 times as large as the previous SS tables. So for within, and also, so it creates a SS table every time of a fixed size. So it will maybe like 160 MB, and that is done. So, and that is grouped into different levels. So every SS table will be of a fixed size, and within each level, okay, so you will have many SS tables. Okay, but what it is saying is for each and every SS table, the previous SS table, the number of SS table in a previous one has to have 10 times more SS table in the like for L1, for L0 it was only 1 SS table, level 1. For L2 it will have 10 SS tables maximum, and for L2 it will have 100, and so forth. But the SS table size is fixed in this case, relatively small size. They say it fixed will be 160 MB, but it is not going to be exact 160 maybe, but it will be somewhat around that size. Okay, but the way the compaction happen is when you come to any level, okay, so then when you, but and also one thing it guarantees that in each and every level SS tables are guaranteed to be non-overlapping. So it means that there will be only single partition in an SS table, one SS table. You don't have to go and search for all SS tables. So if you find a partition in one of the SS table in a level, so that's it. So therefore it is read faster. So here you just have to go and look for only one SS table, and there you will surely get all your data, because when it is actually compacting here, okay, so it is looking for all the partitions and then combining all the partitions together in one SS table. But that it was not doing in the size tiered compaction, and therefore the LCS
Here we can label wise doing compaction, right? Means level 1 to 5 we keep in one SS table, then 6 to 10 in one SS table, something like that. It is happening here, right?
Right, something like correct.
Okay.
So, okay, to give a view of how it is done here. So what they have shown an example over here. Okay, so this is one S table, then actually maybe this is an L0 and it is forming an L1 here. So when it gets three of them, actually it tries to compact all of them together in these three. And so this is L1 it is trying to construct. So it keeps on constructing. So whenever it is reached threshold, then it will start for L2. Okay, so when we have already crossed all the 10 SS tables, whatever are required in L1, then it will start forming the L2. So this is the way it will keep on doing for L2. And now if you see the way it is compacting, every time it goes through the whole of this bunch of SS table, and then it creates, gets all the partitions together and form a single SS table. Okay, and then it might combine more partitions also, but that strategy is not very clearly explained here. And then everywhere they say this is a
It
parameter,
is
this is a
trying
property.
to looks like putting merging in one SS table and we reach the threshold, then it is creating another SS table and putting from the old one to new one, something like that.
Right,
And
right. So whenever it finds all the compaction over here, where all the data which is can be merged, then actually it creates a new SS table in the next level, and then it deletes the one on the previous level. So the
Yeah.
compaction is actually created in the next level. So if you look at the one here, like if you have, so here they show that this is L0, this is L1. L0 has only one SS table, L1 has 110, and L2 has 100. So this is all 100 tables, which is almost created. So whenever we want to find any key, and if we get it on first level itself, then we return immediately. So here if we come, so if there is a partition, you just have to go to a single SS table and then you get that partition and then you return. So that is the way actually it simplifies the read load. That is what they are saying. And there is lots of things. And then if you look for the pros, it says that disk requirements are easier to predict because now it is storing all the data sequentially, and a read operation latency is more predictable. But the problem, stale data is evicted more frequently. So that is also done because every time when you do a compaction, you always evict all the stale data, right? Means the tombstones. And the only problem is there will be higher IO utilization and impacting overall latency because we are actually merging all and then going to the next level, and the next level is also trying to merge all of them and again going to the next. And imagine if there were many of these levels, right? So all this process keeps on happening, and therefore there is a lot of higher IO utilization on the disk. Okay, so that might impact the operation latency because every time the disk is being moved from one level to another, so that is an something. And this I think is not what to say by default. Cassandra doesn't use by default, but you can configure it. So that is what this idea. Okay.
Oh,
now,
this compaction is optional, not mandatory.
compaction has to be there, but by default, Cassandra actually
Oh,
this
okay,
is
okay.
a
This
default
option is
strategy.
there.
Yeah.
Yeah,
So
okay,
usually
yeah.
because Cassandra as well as Dynamo, we always look for it as like a more of a available for data right. So therefore this makes more sense because it does quickly write and then gives the CPU processing and everything it releases on that node, right, for us to process the next request. Correct. But in this case, what it does, it's more involved in actually doing all the level by level and moving all those SS tables from one level to another, and that involves a lot of CPU power also.
IO processing is much
IO
more.
process, IO processing more, but to some extent it might have a CPU also,
Mhm.
but always the disk is busy.
Yeah.
And the third one, they talk about the time window compaction strategy, and this is good for a time series data. So what it says is that if we have a time series data, so then we can actually club that together on an SS table. And so if we imagine it is like our what you say, that sliding window approach, right? So if we imagine that this has been configured for an hourly basis data. So every time if we are at 1 o'clock, then you start creating SS tables, okay, from 1 until you reach 2 o'clock, right? If it's hourly base, you want to do compaction. So whatever SS tables you have created from 1 to 2, okay, they will be compacted and that will be formed an SS table and they will be merged actually. And that will be a compacted table for maybe 1 o'clock. Then you start fresh from 2 o'clock, another SS tables. And then when you are done, at the end of the time of whatever your hour or day or maybe month, whatever it is, then you actually merge that for the previous one and you stored that as a compacted SS table. So this is a time series, and I don't think so in the time series we have to you'll have a tombstones or something like that, because it's a time series database, right? It keeps on coming like a streaming data. So I don't know, but this is what is a time series data.
Yeah.
Right. Yeah. So so this they have explained it here, and so like this, so from 10 a.m. you get a mem table you're flashing, and they are like 100 MB. So then at a certain point you say, okay, we have to have only 4 of this table, and then we actually create a bigger one. So we actually compact that, and then we go for the 5. So you can do all these operations till 11, right? And then when you are at 11 o'clock, you actually form a complete SS table of all of these, whatever these were compacted earlier. And so this will be forever. You are not going to modify this. Then you start for 11 a.m. to 12 p.m. like this. And then when you are done with 11 to 12, then you have another SS table for 11 to 12. So these two are actually now not going to be modified at all, but then you start for the next one. And that makes sense for a time series data. So this is what they have explained in this diagram. Yeah. So, and after that, there is another date tiered compaction strategy, and it says it's deprecated in the latest version of Cassandra. But this is also similar to this time window. So again, they are almost declaring same thing like the last hour data of SS table. But what it says is whenever you are, it is actually done based on hour basis. But every 4-hour data is actually compacted into another time window. And that is the only thing difference about it. But this is an alternative to time series data, they are saying. And it is deprecated, so there is not much of information in other places. So that were the 4 strategies. Yeah. Any questions on this? Okay. So now here, and there are some more theory about what types of compactions are. So what it says is the concept of compaction is used for different type of operations in Cassandra. And the common thing about this operation is that it takes one or more table and it outputs a new output SS table, right? And but that so then when are these compactions used? Okay, so the minor compaction, which is actually by default, is triggered automatically by Cassandra. So the minor compaction is what that size tiered compaction strategy, it keeps on doing it. And so this is actually automatically triggered in Cassandra, they say. But then the major compaction, a user executes a compaction over all SS tables on the node. So you might have to do some maintenance. Okay, so then you can have a major compaction. Okay, and that also you can configure based on any of the strategy, and then you can perform that over all the SS tables on a node. Okay, so this is one major compaction. And then you can have a user defined compactions also. So you can, anytime user can trigger a compaction given on a SS table or on a set of SS tables only. So this can be actually user defined. Then they are saying, so what they are trying to show over here is how compaction can be used to address different issues. Like if you want to scrub or fix a broken SS table, so there also you can use a compaction. So then you can remove valid data if the data is corrupted. And if you want to upgrade SS tables to a latest version, then there also you can use it. And if you want to do some cleanup, so then you can do that. or also for doing some secondary index rebuild. So for us, always it was like, getting a mem table to an SS table and SS table doing a compaction. It is there, but you can use compaction for different use cases, and that is what actually they are trying to show over here. Okay, and there are a
It is
lot many
based on
data.
the input data type, right? You need to decide
Right, yeah,
how input is, timing, all that.
yeah. So I also
So
thought it might be more simpler, but it is not. The
No,
compaction
no,
is
no.
very huge.
top is higher. So this broken SS table is like corrupted data, right?
Yeah, so if there is some corruption in the node and all that, so you can actually repair them. And for many things it is, so even they talk about some anti-compaction after repair, the ranges were actually repaired or split out by a table that existed when repair started. Yeah, frankly, some of them I really didn't understand. It took a while for me,
Yeah, but
but
it is
yeah,
a good thing.
yeah.
Yeah, so you have compiled everything.
Right.
And
Mhm.
one more thing, when your SS table is broken, when it will be repaired, so that time no read will happen, right? Or read will happen only from mem table.
No, see these things, every time mem table is okay. You are talking about reads.
Yeah, so
So I
because
think then in that case, it might be the node is out of that ring, and then we are doing some maintenance operation on the node, but we want to push the node back again. Maybe I'm just thinking loud.
How SS table is broken? In which scenario? Like,
broken some data, so offset got corrupted while sending. Offset is in the form 0, 1. I mean, data is stored in
oh,
0, 0, 1, 0, 1, 0,
okay.
1, right? So
Yeah, so I think they are saying that when you are doing parallel writes, when you are actually overwriting and compacting SS tables, there might be chances that it can get corrupted
race
or
around
broken. Yeah,
that
and then
race around condition, right?
yeah.
Multiple users might be trying,
Hmm.
right? Yeah.
So then how do you address those things? So yeah, so it can be used in various use cases. That is what it says. Okay, so then let's move to Tombstone. Okay, so then again the same thing. Why Tombstone? So I found this very interesting, and the way they have actually shown here. Okay, tombstones, and they talk about garbage collections also. But now, why tombstones? Okay, so whenever we want to delete any data in Cassandra, frankly, it doesn't remove it. It just marks that particular data as a tombstone. And why it does that? So there is an example which is given here. So when it says you can do it the way what we do, just go in a table and delete it, right? So here if what is the repercussions of you doing that way? So if we just get a data and we want to delete it, someone would say, why not delete it? Now, if you just imagine we have 3 replicas like this and they have values A, and that value A is replicated across 3 replicas, and then we want to delete A. But by chance, this replica is has failed, okay, and it goes away. At that time, what you'll go to all those 2 replicas and delete those 2 A's, okay, and then you don't delete this one because it is not present at the time. And then when it comes back, so when it comes back and there is a read request, so what this replica will do, it will find, okay, these previous two replicas don't have high value, and then it will do a read repair. Okay, then you will again have these A back, and that is what they say, that this would cause data to be resurrected even if it has been deleted earlier. And therefore, you cannot use or delete just data in most of the distributed way the data stores, right? So therefore, it is better to do a different technique, and that what is the tombstones. So what tombstone does is, if you want to delete an A, so it marks all of them as a tombstone A. So for these 2 replicas, and in this case, the same thing example what they're showing, if this replica was actually down for that particular tombstone marking, so when this comes back now, at that time you get tombstone A, right? So now read repair will happen on this new this replica which came up, not on the other way, and that is the reason you'll have all the tombstones. And this is what actually tombstone is more easier. And then when we have a tombstone, we can actually ignore this value. But then when we are compacting, at that time we can take care of the tombstone, and then we can remove all of them. For that, we'll have to go to all the partitions and get those keys what we are interested in, and then we have to remove them together. Okay, So that is the way we'll have to do, and that will happen only in the compaction. Okay. So therefore, compaction and tombstone usually are discussed together. And that is what the whole thing about the tombstone is. Okay. And so what tombstone, and also what is a good thing about tombstones is this thing what we said about a replica going down and coming up, and also it takes storage space, so you actually can reclaim it by doing a compaction. That is one thing. And it is more performance, improves the performance because you are removing more of the unwanted data and all that stuff. You will do compaction with this. Now they have another thing what is called as GC grace seconds also, because the tombstones are just not removed like that. Okay, so what it says is there is a parameter which is called as a garbage collection grace per seconds, and this is actually for 10 days. So it will keep this tombstone, because this tombstone will also have a timestamp, right? So this tombstones will be in that data, they will be present for at least 10 days till this GC grace seconds, it doesn't expire. So after that only you can actually remove this data. Okay, so the data will still be there, persisted for at least for 10 days. And after that, then it actually will remove them. So if you look at the GC grace seconds, it is 86,400 seconds, which is equivalent to 10 days. And that is what actually it does. And also how it is dropped. So they have given a lot of many different conditions also. But the very basic one is when the tombstones becomes older, then you just do that. Okay, then there are other ways also, there are other complexities also involved, and they're trying to explain it. I really didn't go in details about this, but there is a parameter which you can even change this parameter, and you can configure this to a lower or higher values. So this is what they say. Even if the tombstone is there, even if you have a compaction, it's not going to remove immediately, but it will take some time to remove it, and you'll still see the tombstone present even you have done it at least by default for 10 days. Okay, and then there is another TTL. Okay, what it says is data in Cassandra can have an additional property for time to live. So this is used automatically drop data that is expired once the time is reached. Okay, and so you'll have a TTL for that. And once the TTL is expired, then the data is converted to a tombstone. You know, in some cases you do that, right? So you assign like a time series data. What they say is, so the time series data for each and every SS table, you have a TTL. So how is that SS table TTL used? That is what we are trying to explain. So this TTL, if it expires for that SS table, it will convert into a tombstone, and then it will wait for this garbage collection grace seconds, and then that whole table will be dropped. So that is one example what they are trying to refer here when a TTL used for tombstone. And there are many other things also, but I didn't go in details about that. So this was more about the tombstones. Any questions anyone wants to add on that?
Yeah, it's good clarity.
Right. Okay, now we'll just do whatever we did earlier. We'll finish this session about Cassandra. So in a summary, and I like the way what they have described here, so I thought maybe let's go through it quickly, because it will again sink in our brains and we'll remember it for long. So the summary, what it says, and we all know, is Cassandra is a distributed because it is distributed across different nodes, and then decentralized because each and every node is independent and can take decision on its own. It can decision in the sense it can process any request, whether it's a read or write. And then it is scalable because we can add any number of nodes in the ring, and then they are accommodated. And Gossip does that way, by using seeds and all that. It actually brings up the node, and then the node is scaled, so the load is evenly distributed within the consistent hashing, and highly available. So we know it's highly available, and that is what is the objective of Cassandra as well as Dynamo, and it is a NoSQL database. Okay, and it is designed with understanding that the failures will always happen, And that is what is the key for all the distributed system, but they are actually having that here again. So even if anything fails, at least it's highly available on write. So what Cassandra as Dynamo says, even if single node remains, still it will keep on accepting the writes in an hinted hand of fashion. Okay, but whether it will be efficiently updated and read and all that thing, that is a question mark. But at least it will keep on accepting to give us and to take that objective whatever they have stated earlier. And it is again a peer-to-peer distributed system. So it does not have leaders or followers. So all the nodes are of equal, they have their autonomous, and then they can have take decisions on their own. So they need some way to communicate with each other, and therefore we have a peer-to-peer distributed protocol, that is a gossip and all that. So that is the way it is done. And data is distributed across nodes, and that is very clear, right? So it has to be distributed based on the replicas and everything. And again, the same thing, data is replicated for fault tolerance, redundancies, and everything. And it uses the consistent hashing ring to distribute the data. And then a data model is based on the SS tables and mem tables. So that is what our database engine, data engine or storage engine is. And that uses a distributed feature of Dynamo, okay, and has a tunable consistency. So we looked at the consistencies, right? So the read and write consistency, so we can tune them. So that is not present in Dynamo, but it is present over here. But if we use a higher consistency, then you are actually taking hit on the availability. So then uses a gossip protocol for internode communication. So that is what is discussed. And now, what are the system design patterns what we actually went through in Cassandra? One is the consistent hashing. The second is a quorum, right? So quorum was for actually writing the data and all that based on the replication factor and the quorum size and all that, right? So then we have write-ahead logs. So like the commit log, what we discussed for the writing in any of the nodes. So that is the sort of write-ahead logs, right? So then the segmented logs. So the segmented log, what it actually talks about is, when we looked about the commit logs. So, and we see that the commit log actually keeps on writing data, isn't it? So here in this case, so the commit log, it keeps on writing data, and that commit log is shared across all the SS tables. So if you imagine the SS commit log can keep on incrementing and it can become huge. So then at some point of time, whenever the mem table has written into an SS table, that commit log is actually deleted, right? So how is this commit log written? It says it is actually segmented log. It is not a complete same single file, okay? But it is actually made of separate files, small files, and they have a some threshold, and that is what it says. And then they keep growing, and those number of commit log segments are truncated whenever a particular mem table is written to an S table. So it is a segmented log. That is what it's trying to say here. And now, what is a gossip protocol? So Cassandra, another system design pattern, what is used is the gossip protocol, which we know that it actually uses to inform each and every node about its own status, or actually, share the status of the other nodes, and they all sync with each other and understand what other node capabilities are. And generation number, it is this number is actually used for gossip again. So whenever a node fails, okay, and comes back, so at that time it has a number associated with it, and it keeps on incrementing every time. So whenever gossip exchange its messages, at that time it finds this generation number is higher than what it was for the previous, for the same node, then it sees that, okay, now something has changed in this node, or maybe this node was down for some time, so I need to actually give him more data. And then it understands that and it helps in the gossip protocol to create that difference of that metadata whatever that information is, and therefore it is very useful for gossip protocol intercommunication. So therefore this generation number. And then we saw about the five accrual failure detector. Whenever a node is actually, how do we know if a node has failed? Usually it is just by heartbeat, but we know that heartbeats cannot be the right way to determine a node is failed, because some of the nodes may be of lower capacity, the processing wise, or maybe it's highly loaded, or maybe it has a network bandwidth issue. So you might not get a heartbeat in time. So it doesn't make sense for just to kill the node or say it's a dead node, and then you lose a lot of data, or maybe it will have a lot of confusion in the whole system. So therefore they're using a accrual failure detector mechanism, wherein it will consider all these parameters and really understand the node is still alive and not dead. And so this actually gives Cassandra an upper hand. So it doesn't lose a lot of stuff, as well as same time it keeps the system more stable. And that's very important failure detection mechanism. And it's very complex though, but on a high level, it is that way. It just keeps on looking for the still the heartbeats, but it keeps on adding some delays and says, okay, I'm going to give it some time for it to recover back, or maybe send me a heartbeat again, or maybe after some time I'll say if I get a heartbeat, I'll still consider that failure detection is. And then we know about the Bloom filters, right? So Bloom filters are per SS table. Okay, so each and every SS table will have a Bloom filter, which will actually give us a false positive, saying okay, if the data is not present, if it says, then it means it's not present. But if it is present, it means it might be present. So we'll still have to go and look for that in that. So, but it helps a lot in understanding if the data is not present, because the SS tables are also big. Then we looked about what hinted handoff is, because whenever a coordinator node actually writes the data itself, and if some of the nodes or the main node is actually failed, so it will keep data with itself, and then whenever the node comes back, it will hand it over. And then the read repair is the same thing. Whenever the node comes back, you will have to, whenever we get a read request, we actually try to repair if we have stale data in other replicas. And then the Cassandra characteristics: distributed, decentralized, scalable, highly available, fault tolerance, and reliable. Then you have this. So these are the very key characteristics of Cassandra, even though some of them are repeated in the Dynamo. So the tunable consistency is the most important thing, which we didn't see over there. And also the geographical distribution, right? So because it is across data centers, and that is a very important characteristic of Cassandra. So it's not only a single data center, but it's about all the data centers, and then you can still coordinate from everywhere. Okay, so this was it. I covered everything what was there in the characteristics till the last of it. Okay.
Yeah.
Anything more?
So what are drawbacks? I mean, what could be drawback? Like you don't have strong consistency here, right? That could be one drawback.
See, well, I look at it, the Cassandra as a complete different use case. It's more for a data value store. Yeah, the faster writes, a data value store, and then they are giving more stress on that wide column, right? So you have an access to all that information based on looking at only one key.
Yeah.
And then you get all that. So that is what they say. Yeah, so the implementation is what they are talking about. But then when you talk about drawbacks, because this use case is completely different, the drawbacks will be the same thing, what we have a difference between SQL and non-SQL.
Yeah, acid properties, basic
Yeah,
properties.
right. So those things will not be present.
I mean, definitely you will not be using it at a place where, I mean, acid compliance is not there, right?
Right.
Yeah.
Acid compliance also, there might be some drawbacks, right? I mean, forget about that. We are comparing with SQL. I mean, in SQL also there are many things, but Cassandra is one of them. So there could be certain drawbacks, no?
Instead of drawbacks, we can say it's limitations. So every component or every tool or whatever you can call this, or data store in all these distributed systems, is designed for a specific purpose, and that is what Cassandra is designed for, like the dynamo. So dynamo is the base for Cassandra's design. So it's more highly available on writes. That's the only key. And it's a wide column. So dynamo doesn't have, I think, a storage engine at all. So here we attach a storage engine, and therefore it becomes a product which we can use as a data store. Yeah. Just the different thing is about the Dynamo. Dynamo had the coordinator node in that Cassandra ring, whatever was that first node based on the partition of our Cassandra, the consistent hashing range. So that was the coordinator node. But here anyone can become a coordinator node in Cassandra. So that is the difference between Cassandra and Dynamo. And here we use, I'm sorry.
Hops you avoid, right, which you used to have in Dynamo. I mean, if some node is not coordinator, you used to take the hops to reach to the coordinator node, which we don't do in Cassandra.
In fact, Cassandra we do, I think, right? If we come to a node,
in Cassandra, anything can become coordinator, right? When client can interact with any node, and that will be the coordinator. But that was not in the case of Dynamo. Dynamo,
well,
it may.
Yeah, that is right. But what happens? See, a coordinator node is any node, but still that's not the replica. We have a replication factor, so it's not in that range. So if a coordinator node was some node like 9 number node, and that request is for 1, 2, and 3 replica, right? So it still has to write in that coordinator node, and then it will forward that request to 1. And then 1 will actually replicate to 2 and 3. So there is an additional hop here in Cassandra.
Okay, in that sense, yeah.
Yeah, but then it gives a flexibility that way.
True. And second limitation, like number of nodes in the ring, because routing table will increase, right? I mean, every node has a routing table which keeps tracks of all information of all the nodes, what all data ranges it is storing.
Yeah,
So
that is there. Yeah.
Even then, you can't increase the number of nodes because routing table will increase, and that will again impact our performance.
Yeah, but still then you can have different rings, in the same data center, what they were talking about, right? So on a different racks, and then you can scale it that way. So that might be one way. I'm not sure. I'm just thinking loud in that. And then you still have it across data center also. So then that is also, I think, is a horizontal scaling, maybe. I don't know. But it becomes more complex. If we look at so much of things about a storage engine, it's not an easy thing.
More of, yeah, we have to dig. Right,
yeah, but for our interview purpose, it is fine. And also we'll have to, it's like the food for thoughts, right?
Exactly.
So something comes in, so there are limitations everywhere, and how we can handle them. If we know more, it is always good. But if we know more, then we really understand that we don't know some of the things again, then it uncovers a lot of things, and then that helps.
Yeah, it depends on use case also.
Right. Okay. Anything else you want to add, or then do you have anything on the chat?
No, in chat there was some questions like generation clock, right?
Okay. Okay, no problem. So then I will stop my sharing.
Yeah, you can stop the recording then.